So we're collecting a bigger and bigger group of functions whose derivative we know how to find. We can take the derivative of any function that looks like a number, a constant, a multiple of x, because that would be a linear function, and x raised to any exponent, even if that exponent is negative or a fraction. Watch how many more functions we can take the derivative of when we know about the sum and difference rules. So great news, the derivative of two functions added together is just their two separate derivatives added together, just like you would hope it would be. So if I have y is x to the fourth plus 12x, I can take the derivative, which I might call y prime, by finding the derivative of x to the fourth, the derivative of 12x, and adding them together. So 4x cubed plus 12. I did another little example here, just to kind of, works with subtraction too. So the derivative of x to the fourth minus 2x squared plus 2 is the derivative of x to the fourth, which is this 4x cubed, minus, because that's a subtraction, this is subtraction, derivative of 2x squared, the 2 exponent comes down to multiply the 2 in the front, the coefficient, to make 4x to the first. And then where does this plus 2 go? Well, the derivative of a constant is 0. And we do not typically add the plus 0 on the end. Although if you did, it would still get full credit. All right, so some practice for this rule here on the next slide. What if I want to find the derivative of this crazy function, which I called g on the slide? Did I also call it g on your paper? Yeah. So just notice I have this parentheses around this expression, all getting raised to this exponent. So we want to simplify that first before we try to see if we have something we can rewrite as x to an exponent. So negative 2x, all raised to the fourth, becomes 16x to the fourth. That x to the fourth in the denominator I can rewrite as x to the negative fourth. Now I'm going to take the derivative, like piece by piece, by adding together the derivatives of each of the terms in this function. All right, another one on your paper. There we go. So find the equation of the tangent line to this function f of x when x equals 2. Well, this is the question I asked you on your last test, except here I never would have given you this function, because to watch you take the limit as h goes to 0 of f of x plus h, you'd have to take x plus h and cube it out and subtract 6 times x plus h squared. That'd be a big algebra mess. But now that we know how to find derivatives, at least of some kinds of functions, watch how fast this problem is. I still need an ordered pair. I know the x-coordinate is going to be 2, it's a comma. I'm going to need the y-coordinate, which is going to be f of 2, which is 4 times 2 cubed. I'm totally going to run out of room. It is not accepted practice to break your statement, your equation over a line, but it's going to happen here. Minus 6 times 2 plus 5. So 4 times 8, 32, minus 12 plus 5. That makes 20 plus 5, 25. Feel free to correct me. I was doing that one on the fly. But where the calculus comes in, this is the beautiful part. Now instead of using the slope of the curve at the point as the limit as h goes to 0 of f of x plus h minus f of x, I can find f prime of x. This is the derivative, right? This is going to be a function that tells me the slope of it, like anywhere I want on the f function. So I'm going to use the power rule. The 3 comes down to the front to multiply the 4, so 12x squared minus 6. Right, the derivative of 6x is 6, and the derivative of 5 is 0. So here's my derivative function. Well, the slope of a line, right, the slope of the tangent line, the slope of the line has to be a constant. So if you ever get asked this question, you have to figure out a one-number answer to use as the slope. If you're writing the slope, we're writing the equation of a tangent line or a normal line. Well, I don't want the slope of f everywhere. I want the slope of f at the one particular place I care about, which is where x equals 2. And the name for the value I want is f prime of 2. So f prime of 2 I find by using 2 in place of x in the f prime rule. It's going to be 12 times 2 squared minus 6. I'm just going to use the order of operations in the correct way. So I'm going to square 2 to get 4. 12 times 2 is 48. Minus 6 is 42. This is my slope. And my ordered pair was 2, 25. So my answer for this example, y minus 25 equals 42 times the quantity x minus 2. Final answer. All right, check out this next one. Find all the points where the graph of x to the fourth minus 5x cubed has a horizontal tangent. Well, tangent line, the slope of the tangent line is the derivative, because the slope of the curve is the derivative. And specifically, a horizontal tangent means a tangent with a slope of 0. So what my goal here is to find a derivative of y, and then to figure out where that derivative is equal to 0. So the slope would equal 0. So I'm going to take my derivative, the derivative of y with respect to x. I can call dy dx. I could also call it y prime. Totally doesn't matter which one you choose. Dy dx is going to be 4x cubed minus, the 3 comes to the front to multiply the 5. 15x squared. You get that right? 15x squared. Okay. So now I want to know where the slope of the function is 0, where the slope of the tangent line makes it horizontal, so the slope must be 0. So I'm going to write this equation, 4x cubed minus 15x squared equals 0. Between now and May 14th, you're going to be at least 100 times where you find a derivative and set it equal to 0. There's lots of problems that we can solve, lots of scenarios that we can answer by finding the derivative of a function and setting it equal to 0. Here's one. If I'm looking for the place where a function might have a horizontal tangent line, so this process you're going to get pretty used to. So now I need to solve this equation. I solve equations degree 2 or higher using the zero product property. That means I'm going to factor and use the zero product property. So the common factor for 4x cubed and 15x squared is x squared. I'm going to factor that out. It's going to make 4x minus 15 equals 0. So either x equals 0 or I should have drawn an arrow. 4x minus 15 equals 0. I'm going to add 15 to both sides and divide by 4. That tells me that x is going to equal 15/4 or 0. So that's a really good start. If you did that on the AP test, you're probably up to already 2 points on the free response section. Remember, you only need about 65 points to get a 5. So if I'm going to read this here, and I want the points. So that means these are the x coordinates. Can I find the y coordinates? So I'm going to start with letting x equal 0, because it looks like that's going to be pretty easy to compute. If x is 0, y is 0 to the fourth minus 5 times 0 cubed. So this function has a horizontal tangent at 0, 0. The 0 came from here, a place where the slope of the tangent was 0. And then I'm going to try this 15/4. Oh my gosh, do I really want to do this? The ordered pair is going to be 15/4. The y coordinate is going to be 15/4 to the 4 minus 5 times 15/4 cubed. Whew. This problem used to be really, 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 really hard. And I make it like one step easier every year. And then this is still. So don't feel like you have to spend time multiplying that out. You would never be expected to. So I'm actually going to write that as my ordered pair. 15/4 to the fourth minus 5 times 15 fourths cubed. And I'll write myself a note for next year to make it even one step less complicated. But you see the process. The locations, the x-coordinates, come from finding the slope, which is the derivative, and setting it equal to 0. I solved degree 2 and higher equations by factoring and using the zero product property. And then once I have those x-coordinates, I'm going to use my original function to figure out the y's that go with them. Okay, so far pretty good. Like, these rules are not too complicated. And I'm remembering, like, all the rules for limits, they work the way I wanted. The limit of a sum is the sum of the limits. The limit of a product is the product of the limits. The limit of a quotient is the quotient of limits. Okay, so now when it's time to answer this one, I have a slide for this. Oh, it's not that exciting a slide. If I want to take the derivative of x squared plus 1 times 2x minus 5, you may not make the assumption that you can take the derivative of each factor and multiply them. That will not give you a correct derivative. But if you remember that you know how to expand this expression by using 4 multiplications, then we can write this as a problem with sums and differences, so pluses and minuses, and we can use the rule, we can use the sum and difference rule for derivatives and just take the derivative of this here. So step 1, notice if my original function is called h of x, and I'm not going to actually do any calculus. I'm just going to reorganize the parts of h of x using algebra. My next line also has that same label, the same label, because I haven't changed h of x. I just am multiplying it out. I'm writing it in a different form, but it's completely equivalent. So it takes 4 multiplications. You can see what I have here, 2x cubed minus 5x squared plus 2x minus 5. Now I want to take the derivative. I'm going to use the power rule here. The 3 is going to come to the front, and it's going to multiply the constant multiplier 2 that was already there to make 6. And my exponent on x is 1 less, so 6x squared minus 10x plus 2. The end.